Professor Dmitry Markovich is a doctor of physical and mathematical sciences and professor and academician of Russian Academy of Sciences. Dmitry Markovich is a director of the Institute of Thermophysics of Siberian branch of Russian Academy of Science, named after Kutatiladze. He is specialist in the field of hydrodynamics and heat and mass transfer, wave processes and turbulence in multiphase and reacting media, development of optical methods for diagnostic of flows. A number of new hydrodynamic phenomena were discovered by him, such as stationary solitons on the surface of liquid film, local separation during jet flow around surface, wave formation inside large nonlinear waves. The area of practical applications of research technologies of thermal, hydrodynamic, and nuclear energy, new power sources, aircraft engine buildings. In 2014, he was awarded as a part of a group at the prize of the government of the Russian Federation for the development of scientific foundation, creation, and the implementation of optical animation methods, systems, and technologies for contactless diagnostic dynamic processes to improve efficiency and safety in energy industry and transport. Okay, please, Dmitry Markovich.
Thank you very much, Professor Lyubimova, Tatiana Petrovna. I would like to talk today about the structure and dynamics of swirling flames, optical diagnostics and control. There are two co-authors of this talk, but of course, to obtaining the results, there were a lot of scientists attracted during several years. The outline of my presentation is shown here. I will make short introduction, then we discuss the mixing in swirling jets without combustion, then combustion in the high swirl jet and diagnostics of these flames by different optical methods will be discussed. I will show the results on 3D measurements in such flows, and some aspects of control of the flames also will be presented. A short introduction I would like to make. The flow swirl is often used for the stabilization of flames in different burners, including gas turbine combustors. The reason of the organizing of the swirling flames is the formation of the central wake, or so-called recirculation zone, and flow turbulization, which usually helps to hold the flame, especially for the conditions of high pressures. However, the flow dynamics is rather complex in such flows during combustion, and the reason is the presence of different large-scale vortex structures, which affect mixing, combustion, noise generation, and emissions. So this is the reason of why we started to study such objects many years ago. And here in these pictures you can see the results of different groups, including our group from Novosibirsk and one of the paper is Alexei et al. Started published in 2012, and approximately 15 years we are dealing with this research. So, okay. First, I will stay on the mixing in swirling jet. So we used the stereo PIV systems for velocity measurements, and for diagnostics, the additions and diffusion. We also use the acetone planar laser-induced fluorescence. I will not stay on the details of the measurement systems. They are shown here, but this is, I should say that this is quite modern experimental technique and apparatuses, including different lasers and high resolution digital cameras and so on. This is results, example of results for the hydrodynamics of the cold jet. There is no combustion here. The arrows show the velocity field, and large-scale vortex structures are shown by these blue lines, and typical 4 cases with different degree of swirling. This is not S. This is a swirling parameter. This is jet without swirling. This is low swirl and high swirl up to unit. So the tracer concentration, tracer media concentration is shown by color from yellow to red. And we can observe the ring-like vortices for non-swirling and low swirl jets, and also wake we have here. But for the high swirl jets, the vortex breakdown takes place, and formation of the central recirculation zone occurs. So the identification of vortices is provided by Q criterion here. It allows us to localize the course of vortices. The reverse flow, this is mean flow structure for the same cases, and reverse flow is marked by black line here. There is 2 flow cases of the on the right of this slide, and they are referred to high swirl jets with vortex breakdown. And the flow swirl increases the jet expansion angle. You can see it's here, and provides fast mass exchange near the nozzle exit. For the analysis of planar velocity distributions, we use the POD technique. This is proper orthogonal decomposition, proposed initially for turbulent flows by Lamley more than 40 years ago. And the method of snapshot POD analysis by Sirovich. And POD is, I will not stay on the details, just will say that this method allows to extract coherent velocity fluctuations, and each PID mode represents a linear combination of all velocity snapshots measured in the flow, so they're possible to perform the phase averaging of the pulsations and pulsations of the velocity and the pulsations of the admixture concentration. Okay. So this is typical PID spectra. They demonstrate the presence of two most intensive modes for the jet with the high swirling rate. This regime assumes the vortex breakdown, and it is seen from oops. So sorry, this is just a moment. Okay, I'm sorry. These two modes for the high swirl, red line, this is two POD modes, and they contain a substantial part of the turbulent kinetic energy. And here the corresponding Lissajous figure, this figure shows that these two modes are statistically correlated. And the conclusion is that they represent the two orthogonal cross-sections of the same structure. And in this case, the structure is spiral vortex. There are the first PID modes for different swirl rates, and the conditionally sampled coherent pulsations of the concentration. This is color represented by colors. For non-swirling and low swirling jets, the left figures, the pulsations are nearly symmetrical and induced by ring-like vortices. But for the high swirl jet, the pulsations are asymmetrical, and they correspond to the helical mode of helical vortex structures. So this is phase average flow structure obtained by time average data and conditionally sampled coherent pulsations. I will show extracted coherent structures in these flows, and you can see them by dark color. And for the high swirl, you can see that the spiral vortices can be identified from this experimental data. And based on the assumptions of solid body rotation, this is just an assumption, but it confirms by experimental results. But using this assumption, we can visualize the 3D shape of these coherent structures, and they are shown also in these figures for different swirling. I'm sorry. You can see outer vortex ring-like for non-swirling and low swirl jet here, and inner vortex core for the high swirling jets. And for high swirl, the outer vortex is the outer mixing layer. You can see here it is helix. It is represent helical vortex. We compared obtained results with the direct 3D measurements. I will show the results of the tomographic PIV diagnostics for jets and flames some later. This is high-speed resolution, high-speed diagnostics 3D measurements of velocity fields for the cold jet. This is experimental setup is shown here. So, and jet with the admixture of the acetone. The existence of spiral vortices, of helical vortices, is directly confirmed by this direct 3D measurements with high temporal resolution. High swirl flames, the next part of my talk. This is a description of experimental setup and illumination system for different measurement techniques, the PIV system, OH, laser-induced fluorescence, and formaldehyde LIF measurement system too. The types of different lasers are shown here. I also will not stay on the details of this technique. And this is a description, also short description of the registration system for these methods. And also the different digital cameras are presented, are used for these experiments by us. Okay, the typical regime map for the high swirl flames, this is propellant air case, is shown here. And we can separate the attached diffusion flames, premixed flames, and lifted diffusion flames. Diffusion, I mean, it's the rich flames with the high level of equivalence ratio here. This is typical laboratory nozzle, which we used for these experiments. And this is the case of methane air flames, and this slide shows the visualization and the effect of the equivalence ratio on the flame structure. So this is fuel lean flame, and approximately phi equal to 0.7, and rich flame, this is lifted flame, phi up to 2.5. And this is velocity fields are shown. All these velocity fields are quite similar, except the case of rich flames, which are lifted flames, because at lifted case, the methane air mixture starts to burn at some distance from the nozzle edge, where the rate of mixing with the ambient air is already sufficient for ignition. Okay. And this case, this slide presents the PID analysis of 3 typical cases. No flame case, just jet with a high swirling rate, the lean flame and the rich flame, and this is PID spectra presented here. And for the absence of flame, this is first PID mode, this is second PID mode. The same for the lean flame. Two main powerful PID modes for these 2 cases. But for the rich flame, lifted flame, the third PID mode starts to play a more important role in the coherent pulsations of the flow. And this is examples of results for measurements the concentrations of different radicals. This is OH, laser-induced fluorescence results, and this is formaldehyde HCHO concentration. So OH corresponds to the flame front and concentration of the combustion products, and the formaldehyde concentration corresponds, high concentration corresponds to the flame front. The temporal resolution of these experiments is about 10 microseconds, so the capturing is rather instant, and errors show the vortex structure. I should say that this is simultaneous measurements of the velocity field and the concentration fields in these flows, and this is combination in intersection region. So, and is seen the maximum of OH concentration is in the zone of reverse flow in a flame front, which is located in the inner you see here inner mixing layer. HCHO also visualizes the region of chemical reactions and the flame front, but you can see here the pairs of large vortices. They are seen here, and they are located from the both sides of the flame front, and intersecting region of these two components is shown the region of the maximum local heat release, and also pairs of the large scale vortex structure. It is seen from these pictures. They are deformed as a flame front and affect heat and mass exchange intensity. They provide more intensive mixing of the fresh air and combustion, fresh mixture and combustion products. So I will be faster because time is going on. So this is phase averaged LIF data. So and just I will say a couple of words about the conclusions from these results. And the vortices in the inner mixing layer, they are moving along the edge of the recirculation zone. And they create the conditions where in the close vicinity the local zones appear with a high heat release, more than average values. So, but inner vortex tends to the rising of heat release due to intensification of local heat mass transfer between combustion products in this zone and the fresh mixture. So the spiral vortices are shown here. This is strong helical structure in the flame, and this slide shows the phase averaged. This is PID reconstruction. I should say this is phase average pattern of helical vortex structures. Some visualization based on the reconstructions of planar measurements, and so we can observe because we reconstructed coherent part of 3D velocity distributions. So we can visualize, we can observe the region, this is red color, where the divergence of velocity vector exceeds 0. So this is regions with the essential fall of the local density. And for the low, for the lean mixture, these regions are located in the vicinity of inner vortex. You can see here. But for rich mixture, the regions with the high heat release are located in the vicinity of outer vortex, and exactly this vortex is responsible for the ejection of the ambient air into the fuel air mixture, which comes from the nozzle, because this is a rich mixture. So it requires for combustion ejection of the ambient air, and it is important to say now that existence of such spiral helical vortices is directly confirmed by 3D measurements, tomographic PIV measurements. I already shown you the TOMA PIV results for the cold jet, but next slide I will show. Next slide shows the tomographic PIV system for the flame experiments. I will also not stay on the details, and we performed reconstruction, 3D image reconstruction by our homemade software. And we used hybrid CPU, GPU realizations. This is different kinds of processing algorithms. I also will not stay on the details.
Markovich, 1 минута осталась.
So thank you very much. I will move to finish. So this is data evaluation for laminar premixed flames. So Bunsen flame and the 3D results. And here this is direct measurements of the structure of lean swirling flame. So this is visualization of the flame, and this is velocity measurements, and this is 3D reconstructions of the double vortex structure in such a flow. Okay, flame control. Just I will show a couple of results on the structure of propane air and methane air flames, forcing acoustical forcing was applied for the flow control, and this is results how the flame changes its structure with the acoustical imposition of acoustical waves of different amplitudes and in some range of frequencies. This is a Struhal number, non-dimensional frequency. And I should say that acoustical forcing leads to the change of the this is spiral helical vortex structure, or this is case for the high swirl. And when we apply high amplitude acoustical excitation of this flow, the flow structure is changed, and also changes the combustion process and emission contents. And the last slide shows our recent work on the experiments in combustion chamber. This is on our collaboration with the air engine companies. They need to know the structure of the combustion in the condition of the high pressures, and so this is the installation works, and this is visualization of the combustion for different pressure. Okay, I will not stay on the details, and conclusions of my talk are presented here, and thank you for your attention.
Okay, thank you very much for interesting presentation. Questions, please.
May I ask a short question?
Yes,
okay. Markovich, thank you for interesting presentation. And can you tell, does your results help to improve the design of real burners, or just the more fundamental aspects?
Thank you, Andrei, for this question. Of course, we assume both these aims and fundamental part, and all these years we collaborated very close with the air engine companies, and they use our results for the verification of the numerical simulation of the real real engines, it is applicable for the practice, of course.
Thank you. And one more question about temperature measurements. So the great progress in velocity measurements, but temperature measurements in the fluid volume is still a problem, except maybe with the high temperature gradients.
Yes, thank you. We have methods for the temperature measurements for on the basis of different optical techniques, including laser induced fluorescence, but it is not very simple task. But LIF allows to measure the temperature distributions. Of course, this is not for the industrial experiments, only for laboratory cases or semi-industrial installations, but our methods allow to measure temperatures and also concentration of different radicals during combustion.
Okay, thank you.
Dmitry Markovich, first of all, thank you for your very nice talk. I have a very short question. Your swirl effect always plays stabilizing role for the flame flow. Is it possible, intuitively, it's possible that this effect could be destabilizing? Is it true?
You mean that swirling?
Intuitively, it could be kind of let's say, resonance or for some parameters, if you play with the parameters.
Yes, of course, because during combustion, especially at the conditions of high pressures, the after oscillations can occur, and the swirling of flow allows to control these instabilities. Because if we, for example, will use the just free jet without swirl or with the low swirl, this after oscillations during combustion will be very high, and the flame can disappear in such cases and so on. Swirling helps to stabilize all the combustion in the, especially for the combustion chambers with the high pressure.
Okay, thank you.